So let's do derivation process. We know that x of z equals to dft of r to the negative n times x of n, which means that z transform equals to the discrete Fourier transform of r to the negative n times x of n. If you put r equals to 1, which is the radius of the circle, we will have discrete Fourier transform of x of n. Z transform equals to the Fourier transform in the unit circle. Look, this thing we have done in the derivation of the Z transform equation, if you remember. Let me just walk you through back. We have done this in the derivation of the Z transform equation. At the end we got the Z transform equals to the discrete Fourier transform of r to the negative n times x of n. And then at r equals to 1, which is the radius of the circle, we're going to have x of z equals to discrete Fourier transform of x of n. So just pick this equation. I picked this equation and put it there. X of z equals to discrete Fourier transform of r to the negative n times x of n, which implies that Fourier transform of r to the negative n times x of n equals to x of z. What is discrete Fourier transform? It is a type of Fourier transform. So I just put Fourier transform here. Look, this f is the symbol. It is the notation of the Fourier transform. For the discrete Fourier transform, I put Fourier transform only because ultimately it is the type of the Fourier transform. So I just put Fourier transform here instead of putting DFT. The rest of the stuff is the same. Fourier transform of r to the negative n times x of n equals to x of z. Now to divide the left side and right side by Fourier transform. When you divide the left side by Fourier transform, this Fourier will cancel with the Fourier. On the right side we're going to have x of z, our Fourier transform. And then when you bring this f to the numerator, it becomes inverse Fourier. So I can write x of n times r to the negative n equals to f to the negative 1 times x of r times e to the j omega. Look, as I said, I divide the left side by the Fourier transform. This Fourier cancelled with the Fourier. I left only with x of n times r to the negative n on the left side. On the right, when I divide x of z by Fourier transform, I will get x of z over Fourier transform. And then when you bring this f from the denominator to the numerator, from positive f, it becomes f to the negative 1. What is my Fourier transform to the negative 1? It is the inverse Fourier transform. It is the notation of the inverse Fourier transform. So we're going to put the formula of the inverse Fourier transform here. R times e to the j omega equals to z. Just put r times e to the j omega equals to z and the equation of the inverse Fourier transform. So I will have x of n equals to 1 over 2 pi into integral of x of r times e to the j omega into e to the j omega n times d omega times r to the n. Look, f to the negative 1 is the inverse Fourier transform. The equation of the inverse Fourier transform, if you remember. If you forgot what is inverse Fourier transform, please just go back and check the section of the inverse Fourier transform. The equation of the inverse Fourier transform is 1 over 2 pi into integral of x of r times e to the j omega times e to the j omega n times d omega. This is the inverse Fourier transform equation. For the x of z, for the z, I put r times e to the j omega. Actually, the equation of the inverse Fourier transform is x of n equals to 1 over 2 pi into integral of x of z. I have x of z here, but for the z I put r times e to the j omega. Where this r to the positive n came? It is this r. When you bring this r to the other side, from negative n it becomes positive n. Or you can also say that divide both sides by r to the negative n. Divide both the left side and the right side by r to the negative n. Just to get rid of r to the negative n on the left. This r to the negative n cancels with r to the negative n when you divide by r to the negative n. On the right side, we're going to have inverse Fourier transform of x of r times e to the j omega all over r to the negative n. When you bring this r to the negative n to the numerator, it becomes r to the positive n. When you divide the right side by r to the negative n, ultimately you will get r to the positive n. As I said, when I divided the left side by r to the negative n, this r to the negative n cancelled with the r to the negative n. On the right side, I will have r to the negative n in the denominator. This r to the n goes up to have the product with the 2 pi and then goes up to the numerator to become positive n. Whenever you change the variable from the product to the other side, from negative it will be positive, If it is positive, it will become negative. The same thing I did here. I have the product of f. So when I change this f to the right side, from f to the positive one, it becomes f to the negative one. My new equation will be x of n equals to 1 over 2 pi into integral of x of r times e to the j omega times e to the j omega n times d omega times r to the n, which I can write r times e to the j omega to the whole n. Look, I just picked this r to the n from here and put it there with the e to the j omega n. Its power is n. Here the power is n. So I'm going to take n common. I will take a common power for the r and for the e to the j omega. Therefore, I wrote r times e to the j omega to the whole n. As we know that we let r times e to the j omega equals to z. Take derivative on both sides to have r times j times e to the j omega d omega equals to dz. Just take derivative on both sides. When you take derivative on the left side, this j behaves as a constant. We are doing derivative on the left side with respect to omega. So it is like e to the 2x. So derivative of e to the 2x is 2 times e to the 2x. Apply the exact logic here. As I said, r behaves as a constant. Put r as it is, ignore it, and derivative of e to the j omega is j times e to the j omega. Let's suppose if I have 2 for the j, e to the 2 omega. If I take the derivative of e to the 2 omega with respect to omega, I will have 2 times e to the 2 omega. So this j behaves as a constant. Derivative of e to the j omega is j times e to the j omega times d omega, and on the right side I have dz, derivative with respect to z, which equals to j into r times e to the j omega into d omega equals to dz. Now we know that r times e to the j omega equals to z. R times e to the j omega equals to z. So just plug in z for the r times e to the j omega here, which implies that j times z into d omega equals to dz. I just replaced r times e to the j omega by z. I just put z here for the r times e to the j omega. So this term becomes j times z times d omega equals to dz. Now divide both sides by jz to have d omega equals to 1 over jz times dz. Just divide the left side and the right side by jz. So for the d omega, I'm going to plug in 1 over jz dz. Just plug in, just replace this d omega by 1 over jz times dz to have x of n equals to 1 over 2 pi into integral of x of r times e to the j omega into r times e to the j omega to the whole n times 1 over jz times dz. I just put 1 over jz times dz for the d omega here. Now replace r times e to the j omega, r times e to the j omega by z. So my new equation will be, now to replace r times e to the j omega by z, just replace r times e to the j omega, r times e to the j omega by z. So my new equation will be 1 over 2 pi j into integral of x of z times z to the n times z to the negative 1 times z. Look, I have j here in the denominator. So can I bring this j and put it there with the 2 pi? Because we have the product. We have the product of 2 pi with the j. So whether you put j here or here, it is absolutely one thing. I just picked this j and put it there with the 2 pi. Now, I left only with 1 over z. Can I write 1 over z equals to z to the negative 1? Yes. I can write 1 over z equals to z to the negative 1. Here my base is z, and here the base is z. Can I add their powers? Yes. By adding their powers, I will get x of n equals to 1 over 2 pi j into integral of x of z times z to the n minus 1 times z. We know both the terms have the same basis, so their powers will be added. N plus negative 1 becomes n minus 1. And there we got the proof. That's how we derived the inverse z transform equation. This is the inverse z transform equation. X of n equals to 1 over 2 pi j times integral of x of z times z to the n minus 1 times dz, where the limits start from negative infinity up to positive infinity. You can use the integration with the circle as well, which is called contour integration. That's how we were trying to prove, which is the equation of the inverse z transform. And we have derived it here.